There's quite a lot of people online here this morning. Hello, everyone. I think we might get started. So I'd like to say good morning. I'm Carla. I'm the marketing manager here at FuseForward. I'd like to welcome you all to the 7th edition of our webinar series, Remote Control. I won't keep you any longer. I'm looking forward to getting started. So over to you, Mark.
Welcome everyone on this beautiful rainy day in Vancouver, but today we actually have the smoke is gone, the sun is not out, the rain has come, and we are slowly starting to see the fall season come into play and all those beautiful things that come along with the fall in North America. Today I'm going to talk a little bit about digital twins and COVID-19. But in order to go and get us started, I thought I would ask a couple of little polls right now and just get a little feel for people on the call here as to what they know and whether they're familiar with what a digital twin technology is and or what a data commons is. Number 1, for familiar. Number 2, somewhat familiar. Number 3, very familiar. If you wouldn't mind voting, that would give us a little understanding about who we have on the audience here right now. Give you a couple of minutes here, just kind of click your little click.
Yep, I'm watching it here. Nearly everyone's voted. Okay, 90%. It looks like we have 55% of people are somewhat familiar. We have 25% not familiar, and then we have a select few that are very familiar. So a real mix of backgrounds here.
All right, so what I'm going to do is today's talk, I am going to go through and try and use a couple of different examples and talk a little bit about not only what it is, but how it compares to things like other technologies like analytics, AI, ML being machine learning, AI being artificial intelligence, and talk a little bit about those as we move forward. But moving forward today, let me kind of move it along and say, what is a digital twin? Well, let me give you a little bit of a definition. I don't know. See, this kind of looks a little bit like an architectural diagram, but it's actually SimCity. So if you think about SimCity and way that we do gaming is almost creating a virtual world. While it's not specifically the same, it is almost a manifestation of a digital twin. I have a couple of kids. My son loves to go through and play Minecraft. He's creating his own digital world. So we have so many tools and technologies available to create this digital world. But where does a digital twin come into play? Well, a digital twin is very similar to like a gaming environment in SimCity, but instead of being boxy drawings and kitchens, it's actually a real world model of the actual physical world. So it's down to the specific placement of pieces of equipment or even what exists today, and then ways that we can manipulate that to go through and define and figure out what else exists and what could happen to that. And I'm going to talk a little bit about the ways that digital twins are used and some of the use cases around it as we move forward today. So if you look at it, one of the things that always came apart is, well, what's the difference between, say, a digital twin and an aircraft simulation? So a simulator, I have one of my senior partners here. He basically used to work in the aircraft industry and said, you know, we did simulators for aircraft way back in the 70s and 80s. Well, how is that different? And by the way, that was 1970 and 1980, going back on the other century there. But if you look at it, what else can we do right now, and how does it differentiate from an aircraft? So if you think about it, we go in, we put a pilot into a simulation environment to go and teach him how to fly a plane. It's a simulator. You can go through and simulate certain events, but we also went through and put planes into air tunnels, and we're putting specific parts into it. So if you look at something like a drone, we put it into an air tunnel. We can simulate how air flows on the airfoils to go through and figure out whether it's going up and down and how it's actually moving. Well, that's a simulator. But is it close to being it? Well, we always kind of looked at it and said, what is the difference between what we used to do or what we still have available in the way of a simulation versus what a digital twin is? And the way I kind of like to describe it is a simulator is more of a static model of what's going on. It's not dynamic. Whereas a digital twin is more of a dynamic environment of what's going on. So when we think about it, think of going through and putting your plane, and instead of just being in a controlled environment in an air tunnel, you're now going to go through and have it interacting with 2, 3, 4, or 15 additional planes. It's going to be basically dealing with lightning strikes and all those other things in a simulated environment, but we're able to go through and have what we call different kinds of agents and bots interacting with that environment, with that piece of equipment in that environment. That's part of what the digital twin is. So let's kind of look at it. Let's give you a little kind of example of one when I think about it from a building perspective. So we basically, if you're coming from a building world, you might be using a tool called Revit from Autodesk. It provides you with a mechanism to do what's in this diagram of somewhat of a 3D model of the actual building. Then, as we start expanding it, well, what happens if I wanted to go through and add in additional tanking systems? What if I'm going to plug it in with additional environments around that? That's what the digital twin is. It's the ability to take a physical design and a physical model of the systems that are there today. That's what the digital twin part of, and then be able to go through and put different sorts of agents around and work on agent-based modeling to go through and simulate with that 3D model. And then what I like to describe it as, we're starting to move towards a 4D simulation. 4D simulation is, it starts changing over time. And then when we start looking at how it changes over time, what's the impact of system A, say the water flows, with system B, say the HVAC systems or the wastewater systems, and system C, which would be the energy systems. So they all interact with each other, and in a digital twin, we then can start simulating more and more of the interactions with real world flows of what's going on in those systems. And that's where I always like to look at this as a complex environment of a system of systems model. That's what a digital twin helps us to go through and do. Now, everybody kind of comes along and said, well, is this going to take over my job? So we talked to a couple of engineering firms over the last year, and I said, how can this be applied? And as we start moving into this more and more work from home, not everybody in the same room, but we want to be able to interact with environments, what else can digital twins do for me? So the way I like to describe it is, a digital twin is not a replacement for human judgment. Okay, a digital twin is a decision support tool. It's a very sophisticated decision support tool, so you got to know how to ask questions of it, but it is something that's going to help you go through and make better decisions about what's going on inside the systems that you're either designing, whether you're in the construction phase, whether you're in the operations phase, or whether you're in the retrofit phase. There's all kinds of things that digital twins allow you to go through in that process to try and determine what are some better ways of doing it. So let me give you an example. We've worked with a lot of energy plants, and we have a giant turbine in a water flow system. And the turbine is in the middle of the building, and we have to go through and replace the turbine blades. But it's a major overhaul project. And that means that you're basically going to get an energy downtime. You're going to shut the plant down or that turbine down for anywhere between 3 to 5 weeks or more as you go through and do the turbine blades. Well, the key question that comes along when you do that is, what are the exact steps that I need to do, and what are the implications of each step? And as I'm going through the steps of going through and doing the blade replacement, are there additional maintenance programs that I can run at each step in the process? So what a digital twin of the plant would help me do is walk through that scenario. It would go through and show me, as I'm pulling things apart, what all the different steps are, so I can get into a more refined set of maintenance steps so that I can optimize the window. Instead of being down from 5 weeks, I might be getting it down to 4 or 3 or 2 weeks. And I decrease my outage, my outage time. And let's understand, in a commercial context, an outage of a power plant costs a lot of money. So the less downtime that you have in order to go and do your preventative maintenance work, the more that you're going to be able to go through and contribute to the bottom line for the organization and be able to minimize disruptions to customers that might be requiring that power gen. Okay, so let's talk a little bit about the evolution of decision support tools and where do they fit. So I start off on the left with recommender systems, and when I think about that, we actually go back even further before that, where what we're doing is run to fail. In asset maintenance programs, we do things like run to fail systems. We do asset lifecycle analysis. But really, the way I like to describe a recommender system is, you're on Amazon. You're going through and you're looking at a couple of products. And at the bottom, they say, here are what other customers buy. These might be of interest to you. Here are some other things. That's a recommender system. It's using a set of rules to help you to go back and try and identify exactly what different recommendations are for different decision points. All right, let's look at the next phase, predictive analytics. So if you've got a recommender system, it's more based upon rules. But as you start getting into predictive analytics, what we're really looking for is there ways that we can be using different input streams and start predicting what's going to happen next? If you buy X, then you are going to buy Y and Z. So it's a razor. I know I'm going to buy a razor blades in some time. Then I'm going to buy shaving cream. And when you start looking at it, a prediction system might be one where I'm predicting that if this customer is buying this, then what they're going to do is they're going to buy Y and Z every 3 months, every 6 months, and I'm going to start sending them out some sort of decision or selection process to help them come back to keep buying. So those are your purchasing models. But in a predictive analytics also helps us to go through and try and identify kinds of things that could happen in the future if certain scenarios happen. So one of the key questions, a question just popped up, and maybe this is the time to kind of help answer this. How accurate is a digital twin compared to the real world? So let's jump into that as we talk about digital twins here. Okay, in a digital twin, if I've got predictive analytics and I understand some events and I'm forecasting future events, a digital twin is in some cases a physical manifestation of the real world environment. So when I start, we'll talk a little bit about what we're doing, but we actually create in our digital twins real world models of what's going on in the environment. So as an example, the digital twin, to start getting it together, you can create, let's say it's a built environment and it's a building. We will create a 3D model down to exactly where every system is and all the inputs and outputs are in the real world, and put it into a 3D model in a modeling system like Revit. So it's a real world model of that. Then the next question that comes in is, all right, now that's the physical blueprints of it, or the model of it. Now let me start turning on the flow patterns. So in order for us to go through and get flow patterns for that, we start doing a little bit more to those. And that's where it starts looking more and more like a real world model. And so unlike predictive analytics, which is only predicting how a system flows, a digital twin is more giving you a censored environment that is showing how things really do flow. So it's more of, and then you're fine tuning your prediction models, and that then leads us into the evolution of the fifth, which is machine learning. As you start getting in and you have this better model of where things are going, you can start getting into machine learning environments. That means instead of just being strictly predictive analytics based upon historical, we can start looking at a machine or algorithms that basically are fine-tuning their predictions or their forecasts based upon what's actually happening in the real world and based upon understanding the different dynamics of how that system works. So a digital twin helps us with the machine learning, but it's not necessarily machine learning in and of itself can still stand on its own using different types of machine learning algorithms. Now, what about the last? Artificial intelligence. And everybody says, I mean, you listen to Elon Musk, and he sits here and says, the world, AI is going to take it over. And he's worried about things like that. Well, are we? Or is AI still a bit of a remote control model? Is it something that's going to basically know more, or is it just a very more rapid process of rules that actually apply to how things are done? Or is it a set of algorithms coming from machine learning that are basically learning from each other and then making decisions for you? So when we start getting into AI, self-driving cars are the basic example that we're starting to look at today. We start using a kind of technology that allows us to go through and do automated control. Are they rule-based? Perhaps. Or is it more learning from the algorithms, which are a manifestation of rules? Or AI can also start going and doing decision analysis trees using digital twins. So all of them start evolving over time as we get more and more sophisticated with the technologies. But digital twins are a building block, decision support environment for us to help us. And one thing as we move forward, let's understand a little bit on what some of the technologies are, some of the use cases are for a digital twin. So let's look at this right now. And in our recent remote control series, we've talked about virtual operations for control centers. Is there a way that you can run a utility, an electric distribution network, or a water distribution system, or a wastewater collection system, or a gas pipeline, or a building campus environment remotely? Can you do it from home? So I'm sitting here right now in my house. I'm presenting to you on the internet. Okay, but at the same time, I also have a separate network that I can connect in that basically takes me into a private environment to go through and run our cloud infrastructure. Now, all of that is separate, it's private, it's dedicated linkages, it's using virtual private networks. A digital twin now provides this whole environment and that utility or that operations engineer to basically work remotely, and we're able to go through and use that as part of the tooling models now that help us to go through and make decisions for what's happening on premise. So we now have things like robotics. We now have field crews that go in there, but when we have automated control in different robotic systems or remote control of systems, we're able to go through and turn our panels, turn our gauges, and we can do that all remotely. But what we want to do in order to basically help us with those remote operations, we want to use cameras on site. We want to be able to simulate or at least challenge our decisions before we make configuration changes to our production environments. That helps us with remote operations and monitoring. All right, what about safety and equipment testing? I hate to say it, but I keep thinking about the 787 and the Boeing disaster, okay? And I keep looking at it and say, did we actually see all the systems and were we able to go through and simulate all of those different environments? And the only way that they were able to get to root cause is by looking at different simulation models, looking at these black boxes during crashes to go through and say what really happened. And it's almost like a massive investigation process. But if we start looking at it, it's like, all right, well, let's take planes. And we start saying, is there a way that we can take components and start doing safety and equipment testing, not just inside an air tunnel, not just inside a simulator, but actually start putting it in so that it's working in context in very dynamic, high fail environments. It's that 100-year storm. It's that multiple incidences of lightning that might strike the planes all at the same time. Things that people say, hey, that's not really going to happen. It's like, well, guess what? The pandemic that we're in right now with COVID-19 is a 100-year event. So guess what? It's 100 years. 1918 was the last pandemic. Okay, now we're 100 years later, we're in another pandemic, global. So safety and equipment testing is part of that. And how do we go through and be able to go through and test for those 100-year scenarios? And digital twins help us do that. All right, what about situational analysis? So, and I'm not sure if anybody is living on the West Coast right now, but I mentioned earlier at the beginning of my introduction, the smoke. So we have smoke patterns right now coming up from Oregon, from Washington State. I live in Vancouver, and we have them in California. And we have these massive patterns of airflows going across the upper atmosphere that bring the smoke from all the south and up into Canada. At the same time, we have different ways of looking at distribution patterns and where things are going to go. With a digital twin environment of a more regional basis, we're able to look and be able to evaluate what would happen if we put firefighters over here. What would happen if we put all of our firefighting equipment in our planes, dropping all the fire retardant over here? Can we look at what the flow patterns might look like, or the transition, and are going to be able to stop the fires from going? Then the follow-on effects is, as it spreads over here, what about the upper atmosphere flows of all of the different smoke? Where is it going to go? What's it going to do to air quality? Vancouver, everybody talks about gray air quality. Last 2 weeks ago, we were the second worst air quality on the planet. Okay, and yet we had no fires going on, but we're affected by all of the systems south that were causing this bad air quality coming north. So it's all kind of an interesting scenario when we start looking at how can we use digital twins to understand it, and then understand the implications of what we may want to do to help in different scenarios. So what's driving some of the key things? So there's a lot of people writing today articles about digital twins. We got General Electric trying to talk about them for energy environments. We've got IBM doing them for what Watson could be doing for their use. We have different IoT environments that are being done at the same time as well. Okay, so what's causing this massive introduction and popularity behind digital twins? Number one, rapid adoption of sensoring technology. So I've been working with utility companies for 30 years. And we've been working with SCADA systems, analog data controls, metering systems bringing in data. They're there, but they used to be really expensive. Now they're really cheap. I can put a vibration sensor on a pump and be able to get real-time information about how that pump is vibrating to determine potential fail points and whether the harmonics on the pump are such that it's actually performing at optimal speed. Okay, so we've got all these sensors out there. Not only that, but we've now got this massive influx. The more sensors we have, the more data we get. The more data we get, the more ability we have to understand the built environment in which we are actually living and what's going on within it. Okay, so all this data now, and how do we make sense of it? So even though we've got the 3D and 4D images, how do we start going through and making sense of all that event data? All right, the other way that digital twins and what we start seeing is remote management. As we start looking at this and looking at our engineers, and our engineers are living at home, and they're working from home, can they start interacting and doing their design work remotely? But what they do is they need the real world model of what's going on in the built world to help them come up with new engineering systems, or as I mentioned earlier, take the steps in order to go through and do the construction steps required in an optimal way to make sure that the builder or the people in the field that are the field crews are able to follow the 5 steps in the right order and do it optimally. Okay, so that's remote management. And part of that, when we start looking at remote management, that lends us into the health and safety measures. The more that we can decrease people in the field when they don't need to be there and have digital twins to help make those decisions, the less we're going to have contact and have virus spread. So as an example, if you're going to go through and say, hey, I've got to go and put a whole bunch of people on site right now to start working and to basically do a maintenance job, instead of having 10 people underneath that turbine at the turbine plant to go and pull out the turbine blades, I can only have 2 people in there to do job A, and then I can schedule in the next crew to do the actual work on say the bearings at a different point in time, and then I can bring another crew in to go through and do the lubrication jobs and all of the fuel systems at that, or all of the different systems around the fueling at the same time as well. So now it comes into remote management helps us schedule. We then schedule in the field crews to go in to manage health and safety. And then what we're able to do is use a remote crew to go through and actually do the vibration monitoring and be able to predict and be able to go through and start tuning and looking at different tuning parameters on the turbine to go through and manage it using new sensoring technologies and remote controls on the devices and the sensors on the actual turbine itself. So those are just kind of 4 ways of looking at how to interact with this. So as I move along, about halfway through the presentation right now, and hopefully I'm going at a pace that everybody likes right now, and they're able to go through and share some information. But let me go through and talk a little bit about how the digital twin works. Okay, how do you build one? So part of that is there is a process, and we're actually following this process on a couple of our projects right now, and they're part of our ways of creating libraries of elements to create digital twins. So I look at it first is you've got to build one, and you can take one specific one. So let's go and talk about how we would build a digital twin for a building room. And then you can expand it into something bigger. And I'll talk a little bit about how to do that. So let's talk about the 4 steps. Number 1, establish the data environment. So what does that mean? It means you need a data lake. It means you need a repository for all your data. It means you need a place, whether it's going to be a 3D image and you're going to need some building ways of creating that 3D image of what's going on in the systems. I like architectural systems. I mean, I've been working with architects, and I get to go through and look at what they do right now with respect to the presentation of a 3D image and being able to walk through the actual building to see what's going on. So that's part of building the data environment. It's how do you go and capture the line drawings? How do I go through and build that kind of tooling environment to allow me to create a 3D image of what's in the real world, okay? Then we start building the virtual model. So how do we do that? And we've got a research team at one of the universities right now, and it's like, we can't just send people out into the field to do the as-builts. Is there a way that we can convert our as-built drawings that we get from architects as the starting point using things like Revit? Or in the GIS world on a city scale, using things like Esri's GIS products. Those are different ways of now creating that manipulation model where we at least have an environment and map layers or CAD drawings or ways that we can now visualize it. And of course, building the virtual world and the physical, I talked about Minecraft. I also love the world of the virtual reality or augmented reality. Is as we get more and more mature, we go from basically just doing 3D images in an architectural drawing tool or a GIS map to actually getting 3D and 4D images using AR and AV technology, where we're able to go in and basically walk through the different technology into the different worlds. But the virtual world then is what we already have in the way of our current GIS systems. We look at maps and we go onto Google Maps and you can look at it. You can convert the image on Google Maps and you can start seeing the 3D image of it. You can also start going through and looking at the street view, which starts allowing you to move around it, but it's you controlling it. So the third step is to build behavioral agents. Okay, now what are those? So in a SimCity environment where we do gaming, what they've done in that is they actually, when you go away from the game and you're not interacting, they're still having an agent running to go through and show that your building is building. They're trying to simulate some events like, you know, people saying, I've run out of, I've got more and more and I'm using all of my energy, I'm using all my water, I'm using all my wastewater. So you want to go through and build those behavioral agents that are going to be able to continue to simulate or work through the environment. I love visualizing it though. I'm a visual person. So I love to actually have the avatars that are going to go through and say, here's how they're interacting. But behavioral agents are challenging because how do we create Mark's behavioral agent? I think differently than other people. I behave. When somebody pokes me, I do different ways of reacting to it. And so what we start looking at behavioral agents, and one of the things that we start identifying is how do we also start creating ways that we understand how the human beings interact with the systems, especially in a campus environment. Because when you start looking at it, especially what we see is certain people will sit here and say, hey, I'm happy to go and get really close to it, and I'm being close to people. Other people, no, I want to be walking around and I'll walk around people. When you go through and you put a barrier in place, some people climb over the barrier, other people will walk around it, other people will change the behavior and try and drive around it. So those are how we start creating more and more behavioral agents that are going to interact with Step 2's virtual model. Once we have a set of behavioral agents, we have a set of physical or virtual models of the physical world, then we can start running the digital twin. And what you're starting to do is start saying, now I want to program, or I want to start giving those behavioral agents different scenarios that I want them to simulate. What would happen if 1,000 people arrived into the campus all in the same time? How would they interact with the different systems? What kind of different flow patterns would I see on the wastewater and the water and the electric use? What kind of air quality would I have? How do I create a bubble around a person to understand what when they breathe, how far their flow is? What happens if I put a mask on a person, and how much are they going to be going and breathing out? And how much on the receiving end would somebody be breathing in? Those are now scenarios that in Step 4 you can start simulating once you have your behavioral agents and you have your virtual model. And you can start making them work together. That becomes your digital twin. And now you can start looking at, say, well, how do I go and do that? So in a building model or in a single room, it's fairly easy. One of the things we do in the virtual world is we over sensor the room, and it gives us a good behavior so we can understand flow patterns better. So what we've got is, we actually have this done already in one of our Ryerson buildings. We actually have a room overly censored. People coming in, air quality sensors in there, etc. As we start expanding, you put it into an area or a department, and you can start censoring a little bit more. And then you can go in, and there are certain buildings that have been what they call green buildings or over censored buildings, and they become good models for simulating typical rooms and patterns for that. Now, as we start evolving, we start being able to look at how we can scale our digital twins, okay? So what we start looking at is, I can deal with it on an office or an office basis or a campus basis. a building room, a set of buildings within it, and maybe a little bit of how people move between the buildings based upon specific flow patterns, okay? But what else do we have right now besides the office and campus? Can we now build it up into a neighborhood or city? So for the last 15, 20 years, people have been talking about smart cities. I mean, I go back to 2000, 2001. What is a smart city? And we've always talked about transportation patterns on that. Now, I used to belong, I worked with a group out of the University of Waterloo, and we had groups from Toronto come in and talk to us about modeling new transportation patterns and new transportation systems, whether it was rail, increasing the highway patterns across the Toronto city corridors, looking at how to go and put in new types of local and regional transportation systems in place, and what is the best way to spend 20, 50, $100 billion. So now we're at city scale. Now we start asking and said, well, one of the things that we found out from the urban planners is they started designing a pattern model. And they said, well, we're going to deal with it on a regional basis. And when we went in and we looked at their models, it was like, that's great. And then I asked a couple of hard questions. Are you simulating and being able to model out the behavior of mothers and fathers picking up and dropping off their kids for soccer practice before school, end of school, what they do to go down into the small little non-arterial and the local roads, and how the collector systems inside those regional areas are working and within the city and the neighborhood? And it's like, well, no, we're working on the regional basis, and that's what we're looking at. It's like, but you have to model in both the neighborhood and the city inside the city and the intercity relationships in order to understand the different flow patterns for transportation. So what we start doing is, can we create a neighborhood model? And once you do, then I start interacting different types of neighborhoods. Say it's a residential neighborhood, another one which is a mixed residential with high rise, another one which is mixed residential and commercial with different ones in that pattern. And they all have different behavioral characteristics within those different models. And then we start getting into regional and national modeling. And once you've got those digital twins there, we can start going into a bigger and bigger simulation or decision-making digital twin. Worldwide basis. Key thing we've just seen for the last 6 months, or the last 12 months really, is how viruses now dispose or basically distribute on the world stage because of our transportation patterns, the open availability of planes, and even the open borders. We closed borders down, but it's still mutating. But we saw how rapidly a virus, which is no different than the flu on an annual basis, we always had that. But this has been giving us now really good quantitative information about flow patterns and virus spread, not just within an office environment, but within a city environment, within a neighborhood, and between a regional and national basis. Okay, so those are kind of giving you 3 steps in this process. Now, one thing I look at is, how could we now use this knowledge that we have, use this capability of technology, the digitization that we're working on, and what are some innovative use cases for digital twins during this age of COVID-19? And by the way, while we have a current pandemic in us, I don't think anybody is losing sight of the fact that we've always had the flu. It's just not been as pervasive or as deadly as the current one we have. So now, how do we go and use this experience to go through and help us create a safer world and a safer environment and a safer neighborhood and a safer school for our kids? Those are the kinds of things that keep me up at night, keep me thinking about this, and basically precipitated us trying to go through and give this presentation today. So let's talk about some of this, okay? I've got 4 use cases here, and that are just kind of some examples. So I read way too much sometimes, because the more you read, it's kind of like that scary part. You know too much, so you read more, and it gives you more, and you get a little bit more apprehensive of what you're reading. But then the question comes in is, but what can we do about it? So let's take water. There was a project we were part of that was looking at using spectrometer technology to monitor sensors and monitor water flows in real time and measuring the water and the different contaminants in the water against patterns and signatures so that we can do early detection of pathogens in water. Well, once you've got that and if you deploy spectrometers through water systems everywhere, it becomes very expensive. And the thing is, it does get to the point where, is there a better way than doing that? And it does say, we can use digital twins to help us optimize where to put those expensive monitoring systems. We can use cheaper sensoring technologies at different points to keep us early detection systems. So digital twins can help us model the water system. They can help us then understand what would happen if a water inflection point and somebody was basically putting a contaminant in the water stream and where it was going to flow to, given that water goes up and down and you always have a little bit of cross flow, depending upon whether it's a gravity or it's a pressurized system. So digital twins help us to go in, not just simulate the environment, but then also look at the ways that I can turn on taps, turn off taps, look at different flow rates at different points in time during the day. Okay. Second part is basically the facilities. All right, what about this? Now, this is the one that everybody's a little apprehensive on. I've asked questions of our staff here and said, how many people are concerned about going into the office right now? And so we have a lot of people working from home, which is totally fair, and I understand it. And part of it is it's not just the facilities, but it's also the transportation inside the rail cars or the buses that you do in order to get to the office. But in a facilities model, we start wanting to go through and understand the different ways that viruses will basically flow. And if there's a congestion model, at what level of congestion do we have mass flows? So there are people already going through and looking at the different scenarios for congestion modeling. We have that. But what about different ways that we would want to go through and different scenarios we'd want to throw at the digital twin and those behavioral agents? What if 50% of the people were wearing masks and 50% were not? What if 25% of them were kids, 50% were adults, and another 30% were, or 25% were elderly that have immune compromised systems? What would be the flows in that? What kind of level of congestion is appropriate? Is 2 meters the right, or is 1 meter the right amount? Which areas are the right ones? We have basically big scenarios right now for doing that, but what are the different ways that we can basically do that today? Okay. All right, what about renewables? We're already hearing things, and I talked about the smoke patterns right now coming from Southern California and coming up into Vancouver. Well, you got to realize that's a 3-hour flight. Okay, 3 hours of flying time, but we still get the smoke patterns. What happens when we start using renewables? Well, now we start getting into using different ways of looking at pattern and flow and wind turbines. We start looking at ways to go and predict wind flows in different areas to go through and look at optimal placement for new renewable technologies. Whether it's a new kind of in-stream run-of-river project, or whether it is some sort of wind turbine or a smaller wind turbine technology, big, small, medium size, depending upon the turbine size. Those are the other ones. Then I'm going to go into the fourth one here, healthcare. So there are a lot of people right now that have got challenges. Where can we go through and start creating virtual organs? Okay, what are the different ways that we can go through and model the human body and create a digital twin of a heart, create a digital twin of kidneys, create digital twin of lungs? And once we have those, is there ways then of an individual's lungs that you can take your base and then apply how the rest of their systems work with their lungs or hearts or kidneys, and be able to come up with a personalized medical program for an individual, or a personalized organ, so we can understand how it's going to work and how their kidneys, hearts, and lungs work. Those are virtual organs. All right, so let's go through this a little bit now, and let's talk about some specific examples right now related to this. So air quality. So I've looked at the world of digital twins, and the first one that keeps me up at night right now is, how do I make the schools for the kids safe? We have in Canada the government announcing $1.5 billion of new money for HVAC systems and air quality systems in schools. we just went in and retrofitted our own offices right now with new localized HPV systems. Like there are HVAC systems which are targeted towards rooms and start creating more airflow within the room model that's bringing in outside air and getting rid of the inside air and recycling the air. So we start looking at it. Most schools right now, do they have those systems? Well, not if they're 50 years old or 60 years old. So we then start looking and say, well, what happens if? What is the right way to implement new HVAC systems? Or is there a way that we can retrofit some of our HVACs by putting in new pipes and new intake airflow systems without just opening up windows, so that we're refreshing the air cycles, we're taking out the bad, we're going through and monitoring, and then even into the air quality, as we're bringing in the bad air in these new regionalized HVACs, can we also put in a sensor to detect things like COVID or other types of viruses while we're also going through and bringing that air and recycling the air? So there's a real world example of air quality management today. The sensor's available, but as we start looking at it, we want to optimize the use of $1.5 billion or more and say, where is the best use of those funds? Instead of just trying to throw the money, is there ways that we can retrofit in a very optimal way to go through and use that money for the best use and at the best return on investment? All right, what about infections in wastewater? Okay, so infections of wastewater. So there's been some interesting, scary articles. They were coming out and saying, you know, we've been detecting COVID-19 in our wastewater back to December 2019. That means that's really when we started seeing it in all these different geographies. That means it was actually out in the wild already, as they describe it, because that is a leading or a lagging indicator of what's going on. I'm not going to tell you how your biology works, but let's just understand wastewater is a lagging indicator. Now, what does that mean? So in all of our labs, when we go through and do water quality monitoring and wastewater, we always have to keep lab results. So we go through and we do sample sets. And in a wastewater treatment plant, they always are going through and doing sampling sets, and they keep the samples for years in some cases because of regulatory requirements, and same with the water samples. So as we start doing this, it starts creating a way that we can start using wastewater as part of the lagging indicator for different neighborhoods as to where there's already is a virus outbreak. We might not even be seeing it, but it now starts targeting certain testing procedures. So in the world of COVID, instead of trying to say it's a sledgehammer for testing, is there a way that we can use some of our lagging indicators to also look at asymptomatic virus outbreaks? So what can be done? So that's where our wastewater systems come into play. It is the lagging indicator. It already shows us in some cases where some of those systems are. Air quality, our air sensors, are more of a leading indicator. It's showing a current outbreak right now. And we start being able to go through and use these to start looking at different flows where people went from households, from neighborhoods, from lift stations in the wastewater systems to determine where the wastewater came from and where the different sampling points are so that we can look at the sample sets that came with that. All right, what else can we use this for? Well, this gets into supporting safe reentry. Okay, so when I look at it, I have a wife, she works in the healthcare world. And one of the things she says, I feel safer, Mark, going into my office at the hospital than I do going to one of the grocery stores right now. And I said, why is that? It's because in the environment in the hospital, they already have protocols and they're very regimented in their protocols on going through and monitoring and managing their environments, okay? Now, what about in buildings? Do we have the same thing? What about in grocery stores? No, it's more what we call in the wild. So once you're in that and you start moving away from a hospital, which is very regimented protocols, to an office, which is a little bit more regulated and regimented, to a grocery environment where we have more people interacting that's never been understanding what protocols are, to the general, say, the environment out there, which is just a street party, okay, where there's no controls at all. And you start understanding what we need to be managing and monitoring and how we can now simulate that to understand safe reentry. So we're already starting to see that a little bit in the protocol management and the way that we're dealing with COVID-19. So instead of going through and saying we're closing down the country now, we're now saying, can we close down part of it? If we see an outbreak, can we go and focus on that area? But again, when I talked earlier about the first two, what are the leading and lagging indicators that we want to be able to use in order to understand what's going on? But in a digital twin, we can use that to actually help understand a hospital or a really protocol-driven environment. How is it going to work? Semi, a little bit less, and not rigid at all. And you now see that you have different things in a digital twin that you can now simulate, and then you can start basically putting in and say, what happens when we have all four of these working together? What are the kinds of questions that we want to throw at it to determine what's going on? Now, going back to this, I now look at it as like, where are we going to go in this world? And I've been in discussions with a couple of doctors and some life sciences chief science officers over the last month. It's been a very, I enjoy those conversations because it gives me a great little learning experience myself. Because I start looking at it's like, how are you guys using this? Are you using digital twins? And some of them come up with an example that I want to go through and do a digital twin of an emergency room so I can look at different ways of using PPE or personally protective equipment and how I can use that and what is the right way and what's the optimal way of using that and having the interactions between the technicians, the nurses, the doctors, the patients. And how do we go through and model that? But even on organ virtualization, I always remember the time it's like orthoscopic surgery was new about 25 years ago, and where they were using little cuts in the knee in order to go through and replace it. By the way, I had a knee surgery, so I'm one of those people that have had orthoscopic surgery. And the thing is, they don't have to cut the knee open. They go in with a little camera, and they're monitoring what's going on, and they're working basically remotely. Well, what happens if you want to go and practice that? So this is where organ virtualization comes in, and we start creating a digital twin of the organs or of the knee joint, and we start being able to train doctors and surgeons to go in there and work with a virtual environment of that while they're testing new procedures. And that's ways now where we can use organ virtualization to help us do that. The same thing is, what if we want to go through and look at the interaction between the different organs and we want to apply different pharmaceuticals or chemicals against them? So, because we always look at it and say, what are the side effects? So even as we start looking at treatments and we start looking at virus, the side effects of different immunization techniques, what are the side effects that we're going to be looking at on that? And can we use organ virtualization or body virtualization to determine whether there's going to be side effects with respect to taking it in? If you're going to see some pharmaceutical attacking the lung and helping to go through and address an issue in the lung, is it going to have a problem with the kidney? Is it going to cause the kidneys to fail even though the lung might be getting better? And then what are the side effects that go with it? That's where organ virtualization and the interactions between those systems starts coming into play, and you can start using digital twins for that. So I'm coming up to the end, and what I'm going to do is just share a couple of key points coming up. I see a couple of minutes here that I've got, and I've got about 2 or 3 things, but I want to share a little bit. It's just the real world on this, okay? So a lot of people may be going through and saying, this is not applicable to me, I can't make this work. Well, we're actually making it work. We've got a project, it's built upon about 3 years of historical research work with a number of university labs in Canada. Different ones that were working on big data analytics. Another university was working on computer science and different mathematical models. And then a third, which is related to people that have got engineering, architectural backgrounds, and GIS backgrounds, and civil engineering. The civil engineering, that one I'm talking about is Ryerson University. So we have 4 different labs at the Ryerson with different professors with different backgrounds. We're augmenting it with another group out of a big data program at Simon Fraser University, and we're building the world's first, I don't know whether it's the world's first, but it sounds good, intelligent campus. But what is that? It's not just the campus itself, it's basically being able to go through and take 3D images and build the whole campus in a virtual world, aka a digital twin, censoring it, pulling in all the readings from their real-time control systems, and then start being able to visualize what could go on inside that environment. So what are the things we're looking at? So Ryerson University is in the middle of downtown Toronto. It's right on Yonge Street, but not there. It's one of the few universities that is actually in a downtown core where the students have to interact with the general population and move between classes all the time. It's not a controlled entry environment. So it's got a lot of other dynamics with it. So you've got buildings which people are moving between it. You got different residences living right next door to a university building, and you basically have the whole downtown core and the entertainment district close at hand. So now we start looking and say, can we understand the flow patterns of people in and out of the buildings? Can we look at it within rooms? Can we look at what happens when they distribute outside? Can we then simulate and visualize what would happen if we did different things to that building, to the way that the buildings are connected to each other, and the ways that we could be scheduling different classes, and instead of forcing groups of students to go between all the different buildings across different blocks in the city, we can start figuring out how we could schedule more and more of the same cohort within a certain set of buildings. So we're doing cohort-based scheduling, similar to what we're doing at our soccer teams, similar to what we're doing in our schools today. So part of what that does is it helps to go and look at the environmental performance of the buildings. We're also looking at ways of reducing traffic congestion, and not just cars, not just buses, but also traffic congestion with respect to people. And then the key one that we've also started to do, and we've already got our researchers right now in their buildings, they've already found ways to use what we call dynamic set pointing on HVAC systems to control basically the room and the energy use within it. So instead of creating fixed set points on a thermometer or a thermostat, where you'd say, I want it at 78 degrees Fahrenheit or 22 degrees or 20 degrees Celsius in the morning, and I want to change it in the afternoons, I can start creating dynamic set points to change it based upon the density of people within a room, and start looking at that. And that starts saving it by using dynamic set pointing and algorithms that we can then verify inside the digital twin. We're able to go through and save upwards of 20 to 30% energy use within the building by doing that and using dynamic set pointing. So that's our Smart Campus digital twin. We're currently working on, we started off about 2 years or a year and a half ago at a room level. We're now into building level. We're currently streaming all the data into a virtual lab environment in AWS and Amazon Web Services. And we're starting to go through and look at collecting more and more models to create building blocks of different campuses as well. So that if somebody wants to build a digital twin of their own campus, we're starting to create components and building blocks to go and do that. So we do have a little bit of a call to action here. How do you start a digital twin project? So I already told you about the 4 steps you can do to get there. Do you need to start at a whole campus level? No. You can start with something smaller. You can start with a building. You can start with a room. You can start with taking a restaurant in a restaurant chain and starting to go through and look at the data streams that you're looking at, model the scenarios that you want to be using, and using your digital twin to go through and do that in real time, and then help you to mitigate your COVID-19 risks. So we're here to help as you require. We have a website here. If you're interested in a digital twin pilot, learning more, please sign up. We can give you information on what we're doing today. We also have some ways to go and bring in other organizations that may want to start one. And we do have also different funding envelopes that we have, especially in the Canadian market, but we also have some different partners in the US as well that can also be working on digital twin pilot projects as well. So with that, I want to turn it over, and we've got a few minutes here for some Q&A sessions, and if there's any questions from the audience.
Hi, we have a couple of questions there, Mark. The first one from Sorav, and I hope I'm pronouncing that correctly. He has a system that guesses the state of the grid every 30 minutes using a limited set of data. And he is asking, is this already a digital twin, or what is missing?
I'm just reading the question right now to kind of get my head around it. So updates a few minutes, 30-year-old technology combines limited measures. Yes, it is. It's the beginning of it. So then this guess state is used for various what-if scenarios every 1 hour. So let's go through and look at electrical grid transmission analysis. So I always look at this as digital twins. We have simulators out there that do certain portions of this. And given I come from a background of working with utility companies, I'm very much aware that a lot of our SCADA systems and our real-time control systems are already out there. with certain reaction points to that. Now, where a digital twin comes in is what you have then is a beginning basis for that. But if I look at an electric grid transmission, I look at situational analysis. If I'm looking at an electric grid and I want to understand power dispatch, and I want to simulate different ways of doing power dispatch and understanding the load on the grid, that's where you start adding more and more what-if scenarios to the digital twin. So you have a basis for that in what you have in the way of the data sets and part of that technology. Now you start going through and saying, now, can I expand it more to be able to create different agent-based interactions with that environment that you've got and use that data to help you? But then can I start having it so that I can now ask it more questions? And that's where the digital twin comes into play. So I've got another question here. How big data is utilized? How is big data utilized to refine a digital twin? So I love this one because I've learned a lot over the last 10 years. And we were using smart metering technology at one point with that was getting data from the field with a smart metering project. And we were using electric meters. We installed a set of district flow meters, and we were also using water meters at the home for consumption information. And we used district flow meters for the wastewater. And what we did is we said, okay, well, let's start collecting it. What the premise behind this was, let's create an over-sensor environments, because once we over-sensor environments, we're able to collect more meaningful information to actually help us create the agents and the behavioral agents that simulate with the environment in a much finer level of detail. So one of the things that we learned back then was a lot of the metering technologies that we have that might be collecting a lot of consumption information from homes for billing data for smart meters in the utility world are not tuned to give us per minute or per second flow information. That means it's throwaway. That means that we don't have it down to the granular level, and it wasn't giving us enough pattern-based information. So it goes back to the last question a little bit on electric. It may give you hourly based changes or even daily changes, but it doesn't give you per minute changes. That means you can't necessarily simulate or use that data to help you. But with big data, the more data we get from logging and real-time readings, the better we're able to create the agents that we can then throw at the system to interact with it. Once we have those agents, we're able to then apply more algorithms to the agent so that we don't need as much big data anymore, and we can now use those as learning agents. That's where ML comes in, and our digital twin becomes more and more sophisticated. Hopefully I'm answering the question there.
Great.
Any others? I think we've got a couple of minutes here, and on that note, and by the way, there was some questions about whether this presentation will be available online. Yes, it will. We always post all of our remote control series. And with that, I want to send it over to Carla to kind of wrap up a little bit and share with you a few more details on what's coming up.
Yeah, thanks, Mark. That was a great presentation. And thanks everyone for joining us. It was great to have you with us today. Remote control is part of a series. So this is the 7th edition. We have one coming up towards the end of October on the future of enterprise asset management. And we'll be taking a look at advancements in this area, including, enhancing your systems using IoT and real-time analytics. So it should be another really interesting topic. If you want to get involved, you can subscribe to our series. The link is here, and Edric will share it in our chat. We're also on LinkedIn, we're on Twitter, we're on Meetup. And if you really want to get in touch, you can email us at marketing@fuseforward.com. So it's almost 12. So with that, I will finish up. Thank you, everyone.
Thanks, everyone, for attending.